Before we get started, I wanted to share with you the use for the Confluence application is used a lot in drug screening applications. So if you're wanting to observe your cells and how they're proliferating with compound screens, this is a very good clean assay that you don't have to do anything but add your cells and your drug, and then you image this plate on Celigo multiple times and you can get growth curves. So that's basically the focus of today, is to show you, first of all, how to acquire bright field images, that you basically are understanding the concept of what a good bright field image is. And then the next we'll show you how to set up the segmentation parameters for obtaining the Confluence measurements. We'll review the data and then save the experiment and then load that same experiment with the plate, so you can show how you can do multiple scanning of the same plate to produce your growth curves. And that'll be at the end. We'll basically be able to link multiple scans together to show you growth curves. But the key concept between 1 and 2 are what you can utilize for any application on Celigo. So that's kind of the foundation. So let's get started and start the Celigo. Let me slow this down a little fast. Okay, so first off, let me just point out that the top of the screen of the Celigo software has a workflow diagram, so you can kind of tell where you are in the whole concept of using the Celigo software. And when you launch the software, it starts with the Start tab, and then you progress into the Scan tab, setting up the image acquisition settings, then the Analyze settings, and then if you do any gating, we're not going to today, and then Results is the last tab. So that's the workflow diagram, so you always know where you are in the software. The first thing we'll have to do is log in as a user. So your lab probably has set up unique user IDs for each of you in the lab. You just log in. For this demo purpose, we don't have a password. You just click on login, and we're set to go. And then basically it's bringing you to the next page where we have 4 buttons available to us. The one we're going to focus on today is creating a new scan, the one at the top. So once you click on it, it asks you what is the plate details that you need to enter. So we can image any SBS footprint on Celigo, so you can see all the variety. Today we're going to use a 96 well plate, and it's going to be Greiner 655090. The plates are listed alphabetically. Then we're going to type in a plate ID that's unique to this plate, and then we can load the plate down below here at Load Plate. The stage will open up on the front of the Celigo, and we'll put the plate onto the stage, and then we'll just click OK, and keep your hands clear, because then when you click OK, the stage will move back into the system and will sit at the well location of A1. At this point, we're going to progress over to the Scan tab, and now we're going to set up the image acquisition settings of how we want to take pictures of the wells in the plate. So the first thing we have to do is select an application. That's the only thing available. That's why it's kind of pulsing. It's saying pick this first. So today we're going to use the Confluence application. And once you select an application, the rest of the page starts to set up things to start helping you pick what you need. And the left-hand column here is where we pick the segmentation parameters. In this middle area called the image display area is where the images are actually displayed. And then we have the plate map navigation and selection area in the upper right, and then the well map navigation area in the lower right. So this is general layout for all 4 tabs. So first thing we want to do is set up the system to acquire bright field images. So let's just get familiar with some of the icons on here. So we're going to turn on the live camera. So live will actually be live camera mode, but it's not recording anything. And then we'll want to navigate to a well where we're going to register the focus. So you can see your cells there, but we want to focus on a well that's not on the edge of the plate, something more towards the center. And with the mouse, you can actually pan and scroll in on the image. You can see as I drag around the image, I can zoom in with the scroll button. Now for the illumination settings, that's the next section down. we're going to do auto exposure and gain for bright field. This app works for bright field, not for fluorescence. And the only thing we have to select is apply. It will then try and study the pixel grayscale on the image, and it will return an exposure value that will put us in the middle of the camera range. The camera range is from 0 to 255. Black is 0 and is 255. When you click apply, the software will determine what exposure gives us the camera range pixels of 125, which is right in the middle. So that sets up the illumination for our bright field images. Now we want to set up the focus. How do we want the images to be focused on the plate? Before we do that, I want to show you some of the different ways that you can focus on Celigo. The first is image-based autofocus. This is where the system will actually study the images up and down, like you do on a microscope, to see where the cells are in focus. And then you can see it moves up and down a range of 300 plus or minus. And then once it moves to another well, it's going to try and study and find that same type of focal plane, but at a smaller range. This works well when you have content in every well, if you need absolute perfect focus every time, but it takes a little bit longer. So another mechanism we provided is the hardware focus. And this basically, in the registration well, you see you have a lot of cells for it to initially study, but the other wells have like one cell and it's all the way over to the edge of the well. And there's other wells that are not quite full. So it's a little bit harder to do image-based focus. And so then what we've done is we provided a hardware focus mechanism which studies the bottom of the plate. But on the registration step, it's actually the same as an image base. It will initially study for the cells to be in focus like you do on a microscope, and then it produces 2 LED beams that are reflected at the bottom of the plate. And then it measures these dots between these 2 bottom reflection points. And then it's going to use that distance for every well that it's now going to move to. It says the distance of the beams have to be this distance apart. So if it's further apart, it's going to move up. If it's really too close, then it's going to move further down. So this helps when the system, when the plate is not perfectly flat. The hardware focus is actually a faster mechanism for you to focus on the bottom of the plate versus using image-based focus. So we click the focus setup button and the dialog box comes up, and now we just click register auto. So we're going to first see in the image display area how the cells will go up and down in Z like you see in a microscope. They're going in and out of focus. So it's studying the images here. It's not recording anything, it's just measuring the focus of the image. And when it's done, it will be in the right focal plane when it considers it has the best contrast. And it produces 2 LED beams on the bottom, which you don't see from the user's perspective. And now it's registered. You can see in the orange dialog down below that it's been registered. So now every time you move to another well, it's just going to use the hardware focus beams to find the same focal plane in the next well. It's a little hard to understand, but it's the most common recommended mechanism for us to focus on most of the plate types. Okay, so as you scroll in and move around, you can see the cells are in focus, and there's a lot of contrast on detail on the cells. So you can see this cell that's divided, it's got 2 nuclei that are kind of coming through. Actually, it's almost too much contrast for the image algorithm to work. So let's explain a little bit about the image analysis algorithms. For bright field, this is what a bright field cell looks like, and you can see if you imagine that every pixel in the image actually has a value, and you draw a line over the cell and then plot the pixel value for that line, it looks something like this, where the camera, where you have the image that's black, it's 0 and 255 is white. And then when you draw an intensity threshold value, let me slow this down a little bit. I'll just pause it for a second. So when you have the pixel intensities drawn here in the blue line, and then you have the intensity threshold drawn. It's actually a number that you type in on the left-hand column on the Celigo software. Then it turns on the graphic overlay, which is the green line. So anything above this intensity threshold, it's going to draw an outline around, which is this portion of the screen. So let me play, and you'll see that this here is the same image with the green line drawn around the cell according to that intensity threshold. So fluorescent images are similar, but they actually have black backgrounds. So when you see the cells, it's actually a black background with a very bright center. So this is almost maximized on the camera pixel intensity of 255. So when you draw a line over this cell and you plot those pixel intensities, it looks similar to this profile. And when you have the intensity threshold set at certain value, the purple outline will draw around the cell according to that intensity threshold. So the other algorithm that is on there is dark object, and it's not a very common one that I end up using, but if you want to, it's there. This is how its profile looks when you draw its pixel intensity. And then the fourth one is the texture algorithm. This is basically when you have a lot of cells clustered together, and it's very difficult to kind of segment them individually. So you end up using the Confluence or the texture algorithm, which is in the Confluence application, to draw an outline around the cells because it's looking for a lot of pixel changes in a localized area, which is bigger than a cell. So then it can actually outline around that clustered of intense changes of pixel intensity. So that's how the texture algorithm works. But you can see how the focus is important to establish the bright center of the cell versus the outline of the cell. And when you have too much detail inside the cell, especially for this first one, it's hard to draw a proper outline when you have a lot of pixel intensity changes in the center of the cell. So that's the basic understanding for the image analysis algorithms for how we detect objects in our images. So back at our screen here, you can see that there's just too much detail in the cells, but I can actually adjust the focus a little bit and provide less contrast or less detail inside the cell to help me outline this body of the cell instead of the little punctate objects showing in the cell. So what I call this is defocusing. So it's slightly blurry, and people are a little hesitant. They're like, no, but I want that contrast. But it's really not necessary, and it actually makes a better image when you defocus a little bit. So currently the Z position is at 4.672. We're going to move the stage down. You can just jog by clicking here at the down arrow, and it moves on a micron basis every time you click. Or you can hold this button down with your mouse, just hold it down, and it moves continuously. So we're moving down one click at a time. And as you look at the screen on the right, it's very defocused, and we've lost a lot of that texture on the inside of the cell. This is going to make it much better for counting cells in Brightfield if you chose to use the counting application instead of Confluence. So here we are negative 14 microns from the registration position that the focus setup found. So we'll just click set offset, and now it populates that number negative 14 in the upper dialog up here, and it's basically remembering that after the harbor focus beam focus beams happen, we're going to move negative 14 to take the image. So at this point, we'll now have to select which wells do we want to acquire images in by selecting the selection button and then highlighting the wells on the map in yellow. This is all you need to do to tell the system just to take pictures here. And then we click Start Scan. Okay, at this point, the system moves from the Scan tab over to the Analyze tab, and the left-hand column is updated to populate what are the analysis parameters that should be set. As the system is acquiring images, you'll see the progress bar down below is progressing in percentages to tell you how much is completed. And then the well map on the right-hand side, the wells that we selected that were yellow are now turning green. That means those wells have been acquired and have been saved to the computer hard drive, and you don't ever have to hit save. They're actually automatically saved to the Celigo. By clicking on the well, it actually will populate the image in the display area. This system will take 16 images to acquire the whole well of a 96 well. It will merge the images together so that you can see them all stitched together in the Analyze tab. By turning on the green graphic overlay for Confluence and orange for well mask, you can see with the default settings what is being detected. You can move your mouse around on the image to move the image around and scroll to scroll the image in. Here we're focusing in on the edge of the well where we're looking at the well mask, which is orange. And I want to shrink it a little bit, so just decreasing that % well mask will snug it up right up to the edge of the well. By clicking the Analyze, the graphic overlay it's kind of like hitting enter and it updates the graphic overlay on the screen. So let's just move it out a teensy tiny little bit, 99.2, click Analyze, and then again it updates it. Alternatively, you can check the box on the left that says Auto Analyze, so every time you enter or change a value on the parameters, it automatically updates it instead of hitting Analyze every time. So once you've got your parameters set, I like to drive around a little bit and see how the other wells look. So I'm selecting another well, and once the image is displayed, the graphic overlay is also displayed with these parameters. We zoom in, and I want to just review again the algorithm. So how are we picking these cells up on the image? And at this point, we are focusing on the fourth algorithm on the bottom, which is the texture algorithm. So we're looking at multiple pixel changes in a very localized area, and then it's drawing an outline around the group of clusters that are cells. So this is what we're going to be using today. So you can see when the intensity threshold, the default value for this is set at 15, this is what it's kind of like middle of the ballpark for you. If you want to pick up less area, you just increase the intensity threshold. That's bringing that line up on the drawing, and it will pick up less area. So increasing the intensity threshold picks up less area. So once you're satisfied with the segmentation settings, you just can select selection and select the area space. It highlights all of the wells in the plate, and then analysis settings also highlights the wells to be analyzed with this analysis settings, and then click Start Analysis. At this point, the system will move over to the Results tab, and you can see on here we have the thumbnail images in the display area. And while the system is analyzing each of the wells, I take some time on the descriptions area to start adding content about what is unique about this plate or experiment. And so this is the descriptions plate tab. Then you can see there's a scan tab for descriptions, as well as the scan result, which is your analysis settings. So it might be where you put the cell name, or like if you had a cell type in there, or a drug treatment. The scan is something I might put down like it's a bright field image. I'm only imaging rows B, C, and D for Confluence. And then this is also day 0 scan. These are just descriptions for you. And then the scan result obviously is just the analysis of the image, and we did Confluence today. So the display on the thumbnail is actually the data for Confluence area. So at B2, you can see it's 6.18%. And you can also use the fill icon to actually use the filling in of the Confluence areas to show what was actually detected. So we have very low confluence on the first column, and as it increases to the right, you see more area filled in with green. So that's drawing in the graphic overlay with a fill icon color green. Okay, so this is the thumbnail image for the results. You can see as we move to the right, we're up to 40%. If you want to look at the high resolution image, you just double click on any one of the wells you want to look at. So we'll double click, and in the display area, the whole well for that well you selected is in the display area. Using your mouse, you can scroll in or double click on the image and it populates to a very zoomed in location. And then you can drag with your mouse the image into any area on the well itself. So here is the fill icon as well. So we saw it in the thumbnail view. Now we're going to look at the whole well view. And as you can tell, the green area is shaded with the darker green color. So you can see what is being detected as Confluent and what is not. So just clicking around onto another well, it actually stays at this same zoomed in level and goes to that same area of a well, but in a different well. To get back to the data display, we're going to click back to scan, which is actually the thumbnail view of the plate. And now we want to actually save this whole experience in an experiment. So we're going to click this little save icon down here. And what it does is it remembers everything from the application Confluence, the focus registration, the illumination, the analysis settings. It remembers everything. So we can select this next time when we image the next time point, and we don't have to go through it all again. And so when you want to export images, there's a couple of different ways. You can select a well in the displayed area, zoom into the location that you like, and now you can see, as I minimize the plate map, I would like to record this in a report so I get the image that I want. So we'll turn on what parameters we want to see in the image. So if you want, this is where you would click the save icon here, and whatever's in this rectangular box, it will be saved just like we see here on the display area. And you can save it in any one of the image formats. This is just one way that you can screen grab something for your reports. If you wanted the whole well where it was the raw image, then you click down here with this little icon says export images, and it's basically going to export the bright field image, but it's actually the whole raw image that's coming from the camera. It's not going to have the graphic overlays or anything like that. It's going to be the whole 16 images acquired and stitched together. And you just select where you want to have it stored. We'll put it on the desktop for now. So this is going to be the highest resolution image, which is 1 micron per pixel. The one that's displayed on the image is the pixelation that you see on the image is what you'll see on the photo that we just saved. So this is the first one we captured. We'll open this one up, and you can see it is the same rectangular shape that we saw in the display area. And then when we open up the other image that we saved, this is the whole picture, including the black area that's outside the well. So, but as you zoom in, you can see that the resolution is still very high quality image, and that's the 1 micron per pixel image resolution that was exported. So those are two different ways you can export images for your own reporting purposes for documentation if you want to put it in a publication or a report for project reports. Okay, so let's get back to our results, and I want to bring you back to the plate view. So we'll click the word in the brown box called back to scan. Okay, now we want to put this plate back into the incubator and close this session. So we close this X here, And that brings us back to the Start tab. And then we can eject the plate with this little eject button on the upper icon. So at this point, you would put your plate back in the incubator, let it grow for 24 hours. And then what we want to do the next day is come back and image that same plate so we can see growth. So once the stage is opened up, then you click OK. The stage will go back inside the system. And here we are on the next day. You want to image that same plate using the saved experiment that we had saved on the results tab. So here they'll first create a new scan, and we load the plate category. 96 well. This is an alphabetical list, so we'll have the Greiner 655090, and then we're also going to select the same plate ID that we had from the day before, which is the date, initials, and then Confluence experiment. So it's just a file name, and we're going to associate the 2 days of scans together. So now at this point, this is new. We're going to select the experiment, which we saved at the end, and here in the drop-down menu, you can find your saved experiment, Confluence, Brightfield 96, well, and then click Load Plate. Would you like to perform autofocus registration? We're going to say yes. This is going to open up the stage. We'll put the plate on the stage, and then it'll ask to click OK once the plate has been loaded. It moves back into the instrument, and then it moves to the registration well, which was C4, I think. It will go through the method of focusing like we had seen yesterday, where it studies the Z, and then it places the hardware focus beams on the bottom, and then it'll populate back to the scan tab just like we were yesterday. But at this point, you can see everything is remembered: the application, the offset, the same wells that we had selected. And you can just click snap to see the image display is properly focused and with the correct offset. So everything is all set just like we had programmed it, and we're happy with the focusing that it had returned with the bright center. So at this point, we just have to click Start Scan. So this is the nice thing about saved experiments. It's very little clicking after you've figured it out the first time. You just use the saved experiment, and it remembers everything, even our analysis parameters that we had slightly changed. And then we just click Start Analysis. So at this time, the system will move over to the Results tab, and you can see that the progress bars at the bottom of the page are both moving. So we're scanning and analyzing at the same time. We don't have to wait for the images to progress with the analysis. When an image has been saved to the computer, the system will automatically go ahead and analyze it with the parameters. So at this point, you can put some plate descriptions, information on there. This is a scan tab that is unique to this scan ID. Yesterday's scan would have had the same details that it had for the previous day. So this is a new scan. And you can see that the results for this second scan, it's technically the same because I actually didn't really wait for 24 hours. But here you can see the fill icon is working the same way as I just imaged it a few minutes after I had imaged it the first time. And then you go back to the image with the data view here. And now you can see from up here the word scan, you can toggle in time. So the first scan was at 3:01 and the second scan was actually 3:08. So I can actually change the thumbnails and the data display by just clicking up there and selecting the timestamp that I want to view. Okay, so now if we want to navigate back to the Analyze or Scan tab, say you're not quite satisfied with your analysis settings, anything that has white text up in the progress workflow, you can access that point. So scan and analyze are currently available, but we're okay. Now we want to export the well level data. So you just click up there and then you save this as a file name, and it's a comma separated value file, CSV. So it can be opened up in Excel or Notepad. So we'll give it a plate name. And then for the previous one, we'll also go back to the first scan and export that well level data by clicking on, again, the export well level data icon or button. So we'll just change the name similar, we'll call it scan 1 instead of scan 2. Okay. So what do the CSV files look like? How are they laid out? So let's double click on one of them and open it up in Excel. So this is just one time point. We can see when you open it up, the first portion of the CSV or Excel file is all the details about this scan, the plate name, plate type, the time of acquisition, and then the first section after that is the plate measurements, and we're most interested in the Confluence area, and it's displayed in the same layout as you see on the screen for both CSV files. Now what I'd like to do is draw from our saved experiment. So that's the second brown button on the Start tab. And this is actually saved data in the computer that had a Confluence experiment scan that was acquired for up to 11 days. So we had the same plate imaged 11 days in a row. And I want to show you how growth curves can be created. So you've just seen how you acquire the plate scans for a day-to-day using this saved experiment. Now I want to show you how you can create growth curves on a scan that has been acquired for multiple days. So we'll just select one of these scan times, it doesn't matter which one, and we're going to load the existing scan time that basically has been analyzed already for the Confluence algorithm. So we just click Load Scan. And it populates us over to the Results tab, which shows the thumbnail plate view. And if you click on the fill icon, it kind of gives you a lay of the land of what's in the wells. So we have high density on column 3, and it looks like a twofold dilution as you travel to the right. So now in the scan, you can drop down or click the drop-down menu and see that you can toggle into any of these scan times, and the thumbnail images will update and be displayed. So here at a later time point, you have much more Confluence going on. As you turn on the fill icon, it's pretty much full 100% at the column 3. So we know by the 8th day that we pretty much maximized our Confluence. So I would like to see a proliferation curve for this. Let's go double click on a well first. So if you double click and then zoom in on the full resolution image, this is a really cool feature where on the early time points, you've just plated your cells. Maybe this is the after a day's incubation. You've got these 2 cells that are sitting right here. It looks like maybe they've divided. Turning on the graphic overlay, you can see what's being called out as confluent. But now in the plate map area, you can see the word scan, and here you can also toggle in time. And as you toggle in time, you can see the images update for this localized area that was imaged. So you can see how cells divide just by using this toggle in time feature. It's getting pretty confluent. So this is a really neat growth tracking application. So cell line development people love to look at this because then they can see that it was a single cell at time 0 and it divides every day, or how long it takes to actually divide It's a pretty cool feature. So let's go back to the plate level by clicking back to scan. And then now we're going to create growth curves. So clicking on reports in that same area. Here you have all the scan times for that plate, how many times it was imaged. And when you click on it, it opens up how many times it was analyzed. In this case, it was once. So we want to select which results we want to produce the graph curve or the growth curve in. So we'll select the checkbox for that analysis time frame. And I think day 8 was pretty maxed out. So let's just look at the up to 7 days. And then over here, we're going to select growth tracking for Confluence and then generate report. And here you have displayed for each well its own growth curve. For each day, it's being plotted as a little dot on the graph. And you can change the data display to be a regular growth curve or a normalized, meaning whatever well is that got the maximum, everything else is set that to the maximum of the Y scale. You can export the growth tracking report by clicking an export growth GT report icon and then give it the file a name. It's again also a CSV file, comma, separated value file. And then we're going to save that on the desktop. And we can view that CSV file in Excel, and its layout is a little bit different than what we had seen in the individual time exports. So the data display at the top is a little bit less, but then we go into the growth curve. So we have the doubling time, the doubling rate, and then we have each well's data points stacked together. So here we have B3 for all the data that's being plotted. And you also get your 4-parameter curve fit values down below at the very bottom portion of this well section. And so further down, you have all the wells being populated below that. Okay, so we've covered a lot, but they're really good basic stuff to help you understand how the Celigo acquires good bright field images, understanding how the acquisition of good images and how the algorithms detect the objects in the image using the segmentation parameters. I think that can be applied to any one of the applications on Celigo. And then I showed you a lot of the data reviewing points, how you can export images, export data, and then how you save an experiment, which is very useful if you're going to run the same experiment over multiple times with multiple plates. And then loading the experiment, and then finally we showed you how to produce growth curves. With that, I'd like to open up the forum for any questions for people if they have any at this point.
Thank you, Sarah. I think that was a wonderful presentation. So like Sarah said, we are opening this time up for any questions that our attendees have for us. Just a reminder, you guys are muted, so feel free to type them into the questions bar, and I will receive them and read them out to Sarah when we can get the Q&A session going if you guys have any questions for us. Let's see if any come in. Okay, so we do have one question that has come in. It says, is defocus necessary for fluorescent objects?
Yes, you'll be registering the focus the same way you did in the bright field channel. You'll just be looking at a fluorescent image. You'll click on the focus setup button, and that same little box opens up, and then you click auto register. The system will move the fluorescent image up and down like you would see in a fluorescent microscope until it's in focus, and the hardware focus beams would actually populate there in the image, and the hardware focus beams would be used to acquire the images from there on out. So yes, except for the focus offset would not be needed to do for the fluorescent image. because it doesn't need any defocusing like we had seen in the bright field images. If you do multiple fluorescent channels, the focus offset for those additional channels might be needed. So if you're using hooks in the blue channel and you acquire a green channel as a second channel, you might need to have a slight offset because the fluorescent wavelengths do have different slight focal planes. I do cover that in another webinar.
Thanks, Sarah. We do have another question. Can the hardware autofocus fail in any circumstance? And why are the focusing step distances different in registration well versus other wells?
So the registration well is basically you're telling the system how it's going to focus for the entire plate. The hardware focus works when the bottom of the plate is very flat. And so for instance, a U-bottom plate would not be a good plate for hardware focus because the bottom of the plate is a U-bottom shaped plate. Thick bottom plates that have focal plane, let me just say like a 12 well or a 24 well, the thickness from one well to the next might be slightly different because they're manufactured in a mold. So the thicknesses might be too different for the hardware focus to be having the correct focal plane where the cells are in focus. The film bottom plates, like the black wall, clear bottom plates, those are film that they're very consistent thicknesses from one well to the next. That's the best place to use hardware focus.
Great, thank you, Sarah. Okay, I'm not really seeing any other questions come through. I'm going to give you guys maybe about 10 to 30 more seconds just to see if we get any more questions that come through for us. And while we're waiting to see if any questions come through, I just want to remind our attendees that if you guys have any topics you'd like to see us present in the future, we'd be happy to take any suggestions you guys have for us. There is a short survey you can take at the end of this webinar. It's only 3 questions. And you can write down any of your suggestions there for future topics for any webinars. We'd be happy to hear any of your suggestions. Okay, so we have another question that has come through. It says, is there a way to export images of just a selected field for all 96 wells?
That's a good one. There is currently not a way to do that. But I can put that in as a feature request. I haven't had that one before.
Wonderful. All right. I'm not seeing any other questions. I'm just going to give you guys a couple more seconds in case you're thinking and see if there's anything else that comes through. I think we've had a good group of questions come through so far.
Oops.
All right, I'm not seeing any more questions that's coming through. So if you guys do think of any questions later on that you didn't think to ask right now, you guys can always email us at support@nexilum.com, or you can reach out to Sarah and I. You can give us a call at 978-327-5340. We'd be able to get you in touch with the right person and get any questions you guys have answered for you. Also, just a reminder, as I mentioned earlier, the session today was recorded. So you will be receiving an email with a link to the recording later on today or maybe tomorrow morning. That way you can either watch this webinar again or you can pass it along to a friend or colleague if you wish to share the content with somebody. So I guess that will conclude our webinar for today. Sarah, thank you for a wonderful presentation and thank you for all of our attendees for joining us today. And I hope you guys can join us for our next Celigo user training webinar next month. Thank you,
Thanks,
everyone.
Amy.
Have a wonderful day.
Thanks, Amy. Have a good one, everyone.